Okay, it is my great pleasure to announce the second talk of today's afternoon session, which will be given by Professor Marcelo Lyra, and who will speak about tangential finite-size scaling study of topological phase transition in tetramerized quantum spin chains. Marcelo, time is yours.
Thank you very much. And I would like also to thank you all for participating, attending the workshop. It's been a pleasure for us from the Physics Institute of Maceió to have you following these activities. This work is a part of the PhD thesis of Luan Verismo. And in his thesis, we are trying to focus on the proper scaling analysis of Gaussian-like phase transitions. And we are calling the proper approach for this kind of special quantum critical points as the tangential finite-size scaling. And I hope you can see how it slightly differs from the usual scaling, finite-size scaling analysis that's done in more usual critical points. Here's a brief outline of what I'm going to show you today. Some preliminaries where we are going to stress a couple of recent contributions that we did along this line. And the first one, I will show you a study that we performed on a branched spin chain model that has some very, very interesting quantum phase transitions. And then I will show you very quickly how we could use this tangential finite-size scaling analysis to characterize the critical behavior of Gaussian transition. And then I will also show another paper from the PhD thesis of Luan, where we detailed how this finite-size scaling analysis can be applied to this anisotropic spin-1 chain that has a line of Gaussian critical points. And we are going to compare our numerical results with the field theoretical predictions. And in the second part of the talk, I will show you the work that is on progress now. We are focusing in this tetramerized spin chains. And I will quickly show you experimental realization of this kind of spin chains. And then I'm going to focus on some particular cases. The first one will be for the tetramerized spin chain with two different spin sizes, 1/2 and 5/2. And particularly, we are going to analyze the Gaussian transition that this spin chain presents. And then I'm going to try to look at the possible universality or non-universality of this Gaussian phase transition, considering different spin sizes of at least one of the spin sizes changing from 1/2, that smaller one, until a larger spin size. And by the end, I'm going to show you some preliminary results of the case of tetramerized spin chain with a spin 1 and spin 3/2. This is a very interesting spin chain that presents two Gaussian transitions, and we are also going to characterize the critical exponent, or at least one relevant critical exponent associated with each one of these two transitions. And by the end, I will just quickly draw some conclusion. So very recently, in 2020, we started a model for a hetero trimetallic compound with iron, manganese, and copper ions that could be modeled as an alternate spin chain like this in this graph B, an alternate spin chain, where along the main chain we have a spin 5/2 representing the manganese ions, and spin 1/2 representing the iron ions, and laterally at each manganese ion we have a coupled and spin 1/2 ion that's a copper ion. So this is a typical alternate spin chain with a dangling bond connecting each one of the larger spin unit. And we started this kind of a chain, considering that the coupling between the manganese and the copper ions would be described as an isotropic Heisenberg interaction. The delta here represents the degree of anisotropy of this interaction. And for the J1 interaction along the chain, we considered the two possibilities. The first one was that this interaction could be described by an Ising coupling. And in this case, the full thermodynamics of this model can be analytically obtained using quite a standard transfer matrix approach. And the other case was to consider this J1 coupling along the chain as an isotropic Heisenberg coupling. And in this case, we could do some DMRG calculations to obtain the ground state phase diagram and to look at the quantum phase transitions. So here is a plot of the phase diagram of this model for the particular case on where the lateral coupling is isotropic. So we have here the ground state phase diagram in the plane of J1, which is a coupling along the chain, and the magnetic field H. And here we have superposed the ground states of these two versions of the model, the Ising-Heisenberg version and the full Heisenberg version. So let me try to explain you this line. So this solid line is here, this line here, this other solid line here, and solid lines that are together with this blue, that dotted blue line, and also another line that's together with this blue dotted line. These solid lines represent the boundary between the ground state, the possible ground states for the Ising-Heisenberg version of the model. So the Ising-Heisenberg version of the model shows the ground state with four possible phases. One is a plateau phase on which the magnetization is 3/7 of the saturation magnetization. We have another two plateau phases on which the magnetization is 5/7 of the total saturation magnetization. But these two phases have different spin orderings within the unit cell, and the fully polarized phase. And the phase transitions between these four phases is first order, like in the case of Ising-Heisenberg model. And the dots represent the boundaries between the phases in the full Heisenberg version of the model. So what we see basically is that the first order transition between this gap at the plateau phases splits in two second order transition lines, and in between the plateau phase we have a spin liquid phase. The same occurs for the other transitions between plateau phases, and in particular the short transition line between the two plateau 5/7 plateau phases, it becomes it shrinks to a single transition point. So this single transition point is a transition point between two gapped phases on which the gap closes just at the transition. This is the main characteristic of a Gaussian critical point, and we focused in the scaling behavior at this critical point to obtain the critical exponents. What we did was a very, for us, was a very conventional finite size scaling analysis of the gap in the vicinity of the transition, and we could estimate the correlation length exponent with the high precision, and also the location of the Gaussian critical point. But we have noticed that in the literature that is devoted to numerical studies of these Gaussian critical points, that it is usually said that the standard finite size scaling analysis doesn't work well. And most of the numerical studies, they implement what they call a twisted boundary condition in order to generate level crossing, and through this level crossing, the location of the critical point and the critical exponent can be obtained. However, when we did this analysis, we do not need to consider twisted boundary conditions. So these results are for the usual periodic boundary condition that is used in many situations, and it's a very nice condition or boundary condition because it avoids the emergence of surface modes or end modes in the case of one dimension. So after doing this work, we realized that this scaling analysis near Gaussian critical point was not well settled in the literature. And then we decided to make a very detailed analysis and very detailed protocol to show how this scaling has to be done in general models. And more recently, we addressed this spin one anisotropic chain model, on which we have two kinds of anisotropies. One exchange anisotropy, that's this small lambda, and also local field anisotropy, this capital D. This model has been studied for a couple of decades in the literature, and the phase diagram is very interesting in displaying, including both anisotropies. We have a region where the ground state is the usual neo antiferromagnetic state, a Haldane phase, and what is called the large D phase. The transition between the neo phase and the Haldane phase belongs to the universality class of the Ising transition. The transition between the Haldane and large D phase is Gaussian. So this model has a line of Gaussian phase transitions, and this was very interesting for us to show how this finite size scaling shall be implemented in these Gaussian transitions, and also to test the possible non-universality of these Gaussian points. Let me stress that along this line, we have two very special points. This first point here at the lambda equals to 0 is actually a Costa-Litaulis phase transition, and the end of this line, where the Ising line encounters this Gaussian line, is assumed to be a tricritical point. So let me detail you how this finite size scaling analysis of the gap has to be done. So when we compute the gap in the spin gap as a function of the model parameter, for example, we fixed in this first plot the value of the exchange anisotropy and plot the gap as a function of D for different chain sizes. So in usual Ising-like transitions, what we have here is a crossing of curves obtained from distinct chain sizes. But in the Gaussian transition, these curves do not cross each other, but they just touch tangentially. So what we have to stress in this case is that the slope of these curves are not singular. When we go to longer and longer chains, the slope remains finite. And the usual finite size scaling theory says that the singular part of the thermodynamic or the relevant functions should follow a single scaling parameter or universal form, but just the singular part. So as the slope is not singular, we have to split from the gap curves the slope, and the remaining of the curve is that follows the scaling hypothesis. So this remaining here has to scale as a power law of the system size when you measure it as a function of the distance to the critical point. So how we can explore this form of the scaling behavior where the linear part is split? The usual or the most natural thing to do is to compute the slope of these curves. And the slope of these curves are plotted here in the second plot. And the slope they cross at the critical point. So it's very easy to locate precisely where the critical point is. This is the point where the slope cross. And the second derivative of the gap, is the first momentum of this function that is singular in the thermodynamic limit. So the second derivative, which is plotted here, is the one that becomes singular at the critical point as the system size increases. And if you look at this scaling form, it will give it to you twice the inverse of the correlation length exponent. And when we plot this slope at the critical point as a function of the system size, this will give us a power law from which we can extract with some high accuracy this correlation length critical exponent. To see that this scaling analysis is very accurate, we can then plot all gap data in a single universal form. To do that, we just subtract from the scaled gap the linear contribution. This is the y variable here in this plot, and plot it against the scaling variable, which is the distance to the critical point times the system, the chain size at power 1/nu. So when we plot it in this scaling form, data from different chain sizes will collapse in a single universal form. So this is the proper form to do this scaling analysis of the Gaussian critical point. We have to take care of this linear non-singular contribution before doing the scaling analysis and doing the data collapse. So we did this analysis along the entire Gaussian line for this spin one anisotropic spin chain model. So we located the critical point. This is the critical value of the local field anisotropy for different values of the exchange anisotropy. We computed the slope at the critical point. Look at the slope at the critical point in some places of the Gaussian line. The slope is very small, and this might confuse some previous scaling analysis in the literature, because this linear contribution is small and it can be overlooked when doing the scaling analysis. But note that as we approach the three critical point, the slope becomes even larger and diverges at the three critical point. And this can be used as an indicator of the position of the tricritical point. This would be the position which on where this slope diverges. Here is our set of estimated values for the correlation length exponent, for the inverse of the correlation length exponent. So it is 0 at the lambda equals to 0. At the Costa-Litauer transition, the correlation length exponent is infinite. But the inverse comes from 0 and up to 1.2 at the tricritical point. And we compare with the predicted values from field theoretical modeling based on the nonlinear sigma model. And we can see that our numerical estimates and the field theoretical prediction are very similar. So now we are trying to answer the question regarding to this non-universality of the critical exponents along the Gaussian line or in Gaussian phase transitions. Okay? So in this anisotropic spin-one chain model, we thought that the anisotropies are relevant in the sense that the critical exponent depends on the anisotropy, depends on this Hamiltonian parameter continuously. So we are interested in seeing that what are other Hamiltonian parameters that can be relevant for the universality class of for the critical exponents of this Gaussian transition. And we are now addressing these tetramerized spin chain models, where in the unit cell we have 4 different spins. Actually, we have a pair of spins S1 and a pair of spins S2. And we will consider an alternative exchange coupling. So the exchange couplings between similar spins is J1, and the exchange coupling between different spins is J2. A possible realization of this kind of spin chain models is in this barium-europium compound that has the magnetic couplings, so the main magnetic couplings along a chain, where we alternate a couple of barium ions with a pair of European ions. So this would be an example of a spin chain where we have 2 spin 1 halves followed by 2 spin 5 halves. Why we choose to start this kind of spin chain model? Because we know that they present a Gaussian phase transitions. For example, when we have a spin 1 half and spin 1s, so 2 spins 1 half and 2 spins 1, we have a topological Gaussian phase transition as a function of the ratio between the 2 exchange couplings. When J2 is small, we have a ground state that's mainly trivial. Here is a representation of the correlations in this ground state, where we are using the virtual spin 1 half representation of the spin 1. So each spin 1 is represented as a pair of virtual spins 1 half. So for small values of J2, the ground state has a dimer correlation between the 2 spins 1 half, and also dimer correlations between the 2 spins 1. And as J2 increases, we have a different kind of correlations. So we have correlations between spins 1 half and spins 1. So in this phase here, we will have edge states if we work with open chains, open boundary conditions. And the first phase, we have no bounds, no edge states. In this work here from 2021, they estimated using using twist operators, I believe. And I'm not sure what they did, but they estimated this critical point to be around the 0.762. So we started to study this kind of chains for the, considering the case of spin 1 and spin 5 halves, which is closer to the compound that I showed to you. The phase diagram has a plethora of phases. We have two zero magnetization phases that are with a Gaussian critical point between them, and several plateau phases from 1 until the fully polarized state, each one separated by a narrow spin liquid phases. Let me show you some magnetization curves. So for small values of the ratio between J, it's the ratio between J2 and J1. So for a small value of J, we have a set of plateau phases separated by very narrow spin liquid phases. And for larger values of J, we have the same sequence of plateau phases with larger spin liquid phases. And if you look carefully at the plateaus, you will see very small jumps, like in here or in here. And these very small jumps are related to wedge states, as Professor René showed it to us on Monday. Here's the profile of the magnetization along the chain in the case of zero field. For small values of J, the magnetization is strictly zero all along the chain. And for larger values of J, we have the development of edge states. The magnetization is somehow different from zero at the edges, but it goes exponentially to zero as we penetrate the chain. And just at the transition, this edge modes penetrates slowly towards the middle of the chain. So the edge modes are not actually edge modes, they penetrate in the bulk. So here is our tangential finite size scaling analysis of this Gaussian transition, performed in the same way that I showed you before. We have to split the linear contribution from the curves from the gap curves. The gaps touch tangentially, so we have to split the linear contribution. We computed these slopes as a function of J for different change sizes. The curves will cross at a single point that identifies the critical value of J. And we look at the scaling behavior of these slopes, or the slope of the slope, the second derivative, the curvature of these curves. We see how the curvature scales with the change size. And with this, we estimate the inverse of the correlation length exponent and also the critical point, and put all data in the single universal form in this last plot. So our data was consistent with this inverse of the correlation length exponent being around 1.3, which is consistent with the previous values that we could find in the literature using other kinds of scaling analysis. Well, returning to the case of spin 1 half and spin 1, we can perform the same scaling analysis, and what we found was that the critical point is very similar to the one that was reported last year, 0.7622. So with four digits of precision, so we can compare with the result reported in this paper, 7622. It also too. So our scaling analysis is very accurate indeed, and the correlation length exponent was 1.35. We have still to look at the accuracy of this critical point, critical exponent, to put some error bar. So we are doing this right now. Here is a table where we change the one of the spin sizes. So keeping one spin as a spin 1/2 and the other spin S2, we consider the values from 1/2 to 2.5, 5/2. And what we saw was that the critical point moves continuously toward 0 when this it's somehow expected when this spin 2 goes to infinite, you have some kind of destruction of the quantum correlations, because the spin would be effectively classical. But the main information here is that the correlation length exponent seems to be universal. Our first impression was that the size of the spins is not relevant, is not an Hamiltonian parameter that is able to change the critical exponent of Gaussian phase transitions. It's not relevant. And to finish, we considered the case of spin 1 and spin 3/2. This is a very interesting case. So in this paper from 2003, it was shown that this model supports 2 Gaussian phase transitions. When we represent this spin 1 as a pair of spins 1/2, virtual pair of spin 1/2, and the spin 3/2 as 3 spins 1/2, we can have 3 possible ground states. One ground state where the dimer correlations are just between spins of the same species. Another one that we have one dimer between spins of the same species and one dimer involving spins of different species. And finally, both dimers involve the spins of different species. And as the coupling, the ratio between the exchange couplings change, we go from one ground state to the second one and to the third one. We have two Gaussian phase transitions. And from these 3 possible phases, just the intermediate one generates edge states. The first one and the last one has no edge states, only the intermediate one. Here's a plot of the phase diagram for this model. For low values of the magnetic field, we have just this 0 magnetization plateau, these 3 0 magnetization plateau phases, and a spin liquid phase. And as the magnetic field increases, we find 2 plateau phases, one of magnetization 2, another of magnetization 4, before the final polarized state. And these 2 phases seems to end at a Kosterlitz-Paulus critical points. These phases will this gap is continuously reducing until it disappears. So we are still trying to locate precisely these Kosterlitz-Paulus transitions, but our main focus in the beginning was to characterize these 2 Gaussian transitions to see if they remain in the same universality class as in the previous spin 1/2 and spin S model. So here is our final scaling results for the first phase transition and for the second one. We can locate the critical points very accurately, and the critical correlation critical exponent remains the same. So this is our main result, and let me summarize it. So we are very confident that this tangential finite size scaling analysis of Gaussian phase transitions is very accurate. and it provides the location of the critical point and the correlation length exponent that can be considered very accurate and very precise. And with this final analysis of this tetramerized spin chain models, we are concluding that the size of the spins are not relevant. They are not able to change the critical exponents of these Gaussian phase transitions. And also that in spin chain models that has multiple sequential of Gaussian transitions, they seem to belong to they seem to have the same critical exponent. The universality class is Gaussian, although it's not universal. The exponents change continuously with some parameters, not with the spin size. So it would be interesting to see, for example, in the model that Professor Rodrigo showed to us, that has two Gaussian phase transitions, if they have the same critical exponents, and what happens when these two phase transitions merge at a single critical point. It would be very interesting to look at it together with me. And with that, I end, and thank you again for your attention.
Thank you very much, Marcelo, for very nice talk. The talk is now open for question and comments. So please raise your hand, online participants and the people in the room. If you have some question, just try to give. Maybe until somebody will dare to ask some question. Let me ask two simple questions. First, you use some energy gap for this tangential scaling. And my question is whether you look also whether the energy gap microscopically to which sector it corresponds, whether it was always singlet or singlet triplet gap, because I expect mainly, I'm thinking mainly for spin one Heisenberg anisotropic chain. There was a transition between Haldane phase and the large phase. So I expect over there was singlet, right?
Right. Good. You should say.
It is a triplet.
Spin one
In the zero magnetization sector, with the ground same as the of the sector one. So it's a position between the triplet and the singlet. It's a triplet gap. Not a singlet position.
Because my question concerns, because many times in some system appears that low-lying energy state can belong to the just singlet state.
The same magnetization.
To the same magnetization. So so it was always singlet triplet gap, right?
Between the Ising, the Neo and the Haldane phase, it was in the same magnetization sector.
Yeah, it's because
The gap.
yeah, for example, in the case of the Marcelo equation between the anti-magnetic and Haldane phase, we don't have the. I think you are speaking about the degeneracy of the edge mode, right?
No. I'm thinking just on two energies, lowest lying energies, to which sector they correspond.
What is the relevant energy gap to
Exactly.
consider? So between the Neo and the Haldane phase, it was energy gap within the same sector. And between the Haldane and large D phase, it was between the zero magnetization and magnetization one sectors. These are the relevant scaling gaps.
Okay, thank you very much. And my second question is, I was quite wondering when you say that these two lines, one Gaussian and the
Ising
one, when they touch each other, they touch at three critical points. It should be that they should have like derivative on that point the same.
The literature calls this a three critical point. I do not agree with this kind of naming of this transition, this point. What happens in the model is that these Gaussian lines encounters the Ising line, and after that, this transition becomes first order.
Okay.
When I look to call a critical point, a point where a second line, a line of second order phase transitions and becomes a first order.
Yeah.
This is not actually this case. This case is that the second order line ends, it continues as a first order, but it meets another first order transition line. So it's like two first order transition lines, and the second order line just encounters this first order transition. The literature calls this a critical point, but I also agree with you. It seems not to be exactly what the textbooks call a critical point.
Okay, thank you very much. So let's see whether we have some questions from online participants. Onofre has some questions, so please, Onofre.
Rodrigo,
Rodrigo.
and maybe for the people to learn.
I was wondering if the reason why the exponents, the critical exponents, do not depend on
The spin size.
is it because of SC2 symmetry? Because that's usually enough to constrain the Luttinger parameter, for instance. I'm thinking that beyond Gaussian, it could be like SC2 level 1 was written theory, and then the critical exponents.
This
really
could be an explanation for the size of the spin being not relevant.
Yes.
Maybe. Yeah.
And then at finite magnetic field, what happens to it?
At finite magnetic field, well, at finite magnetic field, these models have no Gaussian phase transition.
Okay.
This spin chain model has no Gaussian phase transition at finite
Okay,
finite
so maybe
field.
there is a way to break the SC2 symmetry
Yeah.
and still have Gaussian transition and see if the
Yeah.
exponents would
Well,
change.
we could see it. We could try to see it at this spin chain model with a dangling coupling. In that case, the Gaussian critical point was at a finite magnetic field. We could try to see different spin sizes to see if the exponent changes. This would be a nice thing to look. Thank you.
Yeah, one more question from Onofre. Please come here just to also to hear from online participants.
Yes, as far as I understand, you consider or you obtain the ground state energy and first or excited energy is numerical.
Numerically, yeah, with the MRG calculations.
Yes. And you can go to this number 200, something like that.
200 sites,
Yes,
for
okay.
200, 300 sites. Spins.
Basically, that was I didn't understand how.
Yeah, it's a DMRG calculation.
DMRG,
Yeah.
okay. And concerning ground state degeneration or first order excitation, it's possible to obtain those.
The ground state is and the ground state and the excited
Ground
state.
state,
Also.
yeah,
Yeah, and the
probably,
first
yeah.
excited state.
First state,
Yeah, the first excited states. If you want the full spectrum,
Mhm.
the MRG would not be very useful.
Yeah. Okay. Yeah, that was my question. Thank you.
Okay, are there any further questions or comments? So doesn't seem so. So let's thank Marcelo again.
Thank you.